All right, so today we're going to talk about this exponential growth and decay. So period 1, I will put exactly when you need to start watching this video. I will give you a time limit on this because I know that we've already gotten through most of this. So for the rest of you, this is our foldable. If you were absent, this is going to be a good help for you. So remember that we write exponential functions in this form. Remember that A is the initial value. It's the y-intercept. And remember that the y-intercept happens when x equals 0. And when we talk about growth and decay, typically it is our starting value. How much did you start off with? Okay. B is going to be our growth or our multiplier. Remember that B is our growth or our multiplier. And when we say growth, we also mean decay, but usually it's the growth rate, right? So when we talk about exponential growth and decay, we're going to take our rate, which is written as a percentage, and we're going to add it to the number 1 if it represents growth. And we're going to take our rate as a percentage, and we're going to subtract it from the number 1 if it represents decay. And we put that in a parenthesis because this is our B value, right? This is our multiplier. And then X is the exponent. And remember, it is the input value. When we talk about growth and decay, this exponent typically is time. It is time, okay? So the formula that we use for exponential growth is y equals A, your initial value, times 1 plus r, 1 plus my rate, just like I set up there, to the power of t. So remember that y is the total amount. It's what you have when you're all done. A is your initial value or your starting value. R is your rate given to you as a percent, and we're going to transform that to a decimal. And then t is your time. Your exponential decay, much like your exponential growth, except that instead of adding 1 and r together, we subtract the rate from the number 1. So we still have this starting value or this initial value. T is still representing time. Our rate is still going to be given as a percentage, and then we're going to have to turn it to a decimal. Okay. So we're just going to start with some examples. So the first examples that we're going to do is just telling us how to deal with this. Okay, so that's what we're going to work with. So if we're growing, remember that we're going to use the plus. If we have decay, we're going to use the subtraction. And I said you need to have your percent written as a decimal. So the way to get around this is if you take the number 100 and then add or subtract your rate, and then whatever you get there, so I'm just going to write 100 plus r, you divide that by 100, and that will give you your decimal. Okay, so we're going to do the first couple like that. So I start with 100. Remember that 100% is the same thing as the number 1. That's where that comes from. Plus 12%, well, that's 112%. Dividing by 100, well, when I take a percentage and divide it by 100, that's how I get the decimal, 1.12. This is a decay, so I have 100%, or the number 1, minus 7%. 100 minus 7 is 93, divided by 100 equals 0.93. Okay, so you can use that method for as long as you need, but I want to show you that you can also think about turning your percent to a decimal at the very beginning, okay? So let's see, 7.5%. If I want to write this as a decimal, I just take the decimal place and move it 2 places to the left. 2 places to the left. So I get 0.075. And it's growth. So I'm going to add that to the number 1. So my B value or my multiplier is 1.075. 5.9% written as a decimal, move it back 1, 2, is the same thing as 0.059. And that's going to be a subtraction problem. So I have to take 1 minus 0.059, and that gives me 94, let's see, 0.941. 0.941, okay? So that's how we deal with finding our rate. So our first example says that we have a population of a city in 1990 that was 1,215,112. This is my starting value. So this is A. My rate, my R value is 5%. And it's growing. So this is going to be a growth. So I take 100 plus 5, which is 105, divided by 100. That gives me the 1.05. So my equation, y equals A, my starting value, 1,215,112, times B, my growth rate or my multiplier, 1.05 to the power of T. Now I want to talk to you about T very quickly. It says that T represents 1 decade. So a decade is equivalent to 10 years. T equals 10 years. So we're predicting the population. So 1 T is 10 years. That's really what I want you to know. So we're predicting the population for the year 2000. So from 1990 to the year 2000, that's a 10-year, that's plus 10 years, right? So that means that T equals 1, because that's 1 decade. T equals 1, that's 1 decade. So I'm going to evaluate my equation, y equals 1,215,112 times the quantity 1.05 to the power of 1. So 1,215,112 times 1.05 to the power of 1 is 1,275,867. Okay. Well, what about in the year 2005? Let's see, 1990 to 2000 is 10 years or 1 T. 1990 to 2010 is 2 decades, right? Or 2T. So to the year 2005, that's 15 years or 1.5 T. So y equals 1,215,112 times 1.05 to the power of 1.5. So I need to put that into my calculator. And when I do that, I end up with 1,307,375. So that's my population in 2005. All right. I think we have 2 more examples. So this first one talks about bacteria. So it says a sample contains 10,000 bacteria. This is A, my starting value. After putting on antibacterial spray, 10% of the bacteria die every hour. This is my rate, and my time is in hours. My time is in hours. So is this going to represent a growth or a decay? Well, we're killing the bacteria, so it's a decay. So I have to take 100 minus my rate of 10%. That equals 90% divided by 100 is 0.9. So that's my rate. So y equals a 10,000 times 0.9 to the power of t. So my first question says, well, if this pattern continues, how much bacteria is going to be left after 3 hours? That just means let t equal 3. So y equals 10,000 times 0.90 to the power of 3. And that means that after 3 hours, there will be 7,290 bacteria left. If this pattern continues, how many will there be left after 1 day? Well, 1 day equals 24 hours. So that means that t equals 24. So y equals 10,000 times 0.90 to the power of 24. So 10,000 times 0.90 to the power of 24 is 797.66. So about 798 bacteria remain. All right, our last example, your starting salary is $35,000 per year. You get a 5% raise every year you stay with the company. So is this going to be growth or decay? This would be a good time for you to maybe pause the video and see if you can do this one on your own. So if you're going to try to do this on your own, pause the video now. So this is growth. 100 plus 5 equals 105. Divided by 100 is 1.05%. My equation, y equals 35,000 times 1.05 to the power of t. My time is in years. So how much money would I make after 2 years? Y equals 35,000 times 1.05 to the power of 2. So when I put that into my calculator, my salary after 2 years is $38,587.50. Not bad. What about when I let t equal 10 years? How much would you make after 10 years? So that's 35,000 times 1.05 to the power of 10. So 35,000 times 1.05 to the power of 10, and that equals $57,011.31. Not too shabby, not too shabby. So that's your foldable. So if we do not get through that in class, you are going to fill that out as homework.